The log-normal distribution is one of those models that is exceptionally attractive because of its relationship to the normal distribution, and that makes it somewhat easy to use. However, it turns out that it's not always got some great properties to it that make it the perfect example of a model. That is, it's an idealized representation, and it may or may not be real effective depending on the particular context that you're looking at. So let's talk about a couple of those contexts where it does tend to somewhat naturally arise. And in the big picture here, there are many engineering models that have products of variables instead of sums. We saw the summation be very useful to us when we were looking at the central limit theorem. So even if the individual random variables were not normally distributed, by the time you sum up a bunch of them by the central limit theorem, you ended up with a normal distribution. And we're going to see a similar kind of thing happen here in terms of products and how we'll end up working with that. Let's look at two very common engineering situations out there. One being when we're looking at the axial force in a structural component. So say we have a bar that is in uniaxial tension or compression, and we're interested in the strength of that bar. Then that axial strength will be equal to its strength in terms of stress times that cross-sectional area. And there we have a product of two random variables, that the area along the length of the bar is potentially random, as well as if you produce a certain bar from bar to bar, that effective cross-sectional area will change. And the stress in terms of its strength, whether that's the yield strength or ultimate strength, proportional limit, whatever you're using as your criteria, is going to be a random variable also. Okay? Another very common situation here where we end up having products is one where we have fluid flowing past an object, and we start looking at, say, the drag force on that object. So the fluid flow has to part around the object, and there are lots of different ways to begin to describe this. One simple way is the drag term of the Morrison model, where we take 1/2 of the density of the fluid times some effective characteristic area times a drag coefficient times then the relative velocity of the fluid flowing past the object. And the absolute value sense here is that we want to keep the sense of the direction of the flow, and sometimes you'll see a minus sign depending on what you've used as your positive sign convention. And there's another term that comes into this drag force, often an inertia term that's associated with whether that object is accelerating or not. Okay? In general, then, where the log normal often shows up is where we have a random variable that is a function of the product of a bunch of other random variables. And let's let that product go up to n in the general case. Right? And so if we take then the natural log of each side, then we get then the sum of those natural logs. And already this starts to look like something that we're used to seeing in terms of essential limit theorem application, right? Because if we go take a look at x equaling natural log of y, then x is going to be approximately normal, as in normally distributed, by our central limit theorem. So that's kind of attractive. And note that when we rework this in terms of y will equal e to the x, which is another direct case of how we get to the log normal, that oftentimes you see it directly posed in this kind of context. And if this is the case, that x has a normal distribution, then y would have then what's called the log normal distribution. And in a graphical sense, let's first put down the typical bell-shaped curve that goes along with the normal distribution. And the mountaintop will be centered right there where my axis is located, and that could be shifted over, of course. And there's your fx of x, your typical PDF for the normal distribution. And then we do the transformation where y is equal to e raised to the x power. And note that first thing that's going to happen is that although x could range from minus infinity to infinity, because of this operation, then y is going to be 0 or larger. And its distribution is not going to be symmetric. Rather, it's going to be, although starting off here at 0 and rising up to a peak, it's going to be a skewed kind of distribution. It's going to have a fat tail out to the right, such that its properties in terms of the mean of y will be shifted over from the mode. Right? Whereas over here at x, of course, the mean is sitting right here on top of the mode, or I should say the other way around, that the peak is right here at the mean. And then in terms of other measures of central tendency, the median of y, sometimes written, the median here is got that little tilde on top of it. Sometimes people put a little upside down hilltop, or they put a U shape on top of this thing. Now median, of course, is the 50 percentile mark, 50% of the area to the left and to the right of the median of that particular value. Right over here in the regular normal distribution, the median and the mean and the mode are all the same value, right? Symmetric distribution with a peak right at the top. Whereas over here in the log normal, that's not the case at all. So we're faced then with an interesting question of how do we handle the various parameters between the normal and the log normal. This is great that when we have products of situations, we can start thinking about it in terms of the normal distribution and easy to use and work with distribution. But the problem really becomes, and all the work is involved in trying to figure out how to deal with the parameters. And so let's take a look at that. That in terms of our parameters, we oftentimes think about a location of the mean in that sort of our centroid of our distribution, and in terms of dispersion, we'll characterize that in terms of the standard deviation oftentimes. Whereas another way to look at that, and very useful in the log normal, is to start characterizing this by the median and then the COV of y. Now this gets to be tedious to write out the COV of y, and so people will have different symbols that they'll use for that. They'll sometimes use little delta, That's not to be confused with the delta that's running around in the Weibull model. And I know this is a pain because it's very confusing. You'd like to think that one symbol means one thing and you don't have to run around and remember all the different contexts, but unfortunately that's just the way life is here, that we have to deal with this. And sometimes this is also given the symbol capital V, which is also confusing because when we use this as an operator with an argument, that's going to be the variance symbol. Yes, very confusing, I understand. And remember, the COV is just the standard deviation divided by the mean. So it's a measure of dispersion in terms of, or in the scale of the mean. Right? Absolutely kind of a pain, there is no doubt, to have all these different symbols running around. And in terms of data needs, though, what we end up really want to work with to get over to our standard normal tables are going to be the mean of the natural log of y and the variance of the natural log of y. And again, that's because we want it for computation, because the natural log of y is normally distributed. And that's a pretty darn key thing here, and why we use this thing at all, even though it does begin to be a bit of a pain to work with. So let's look at what these transformations are. And we're not going to present to you all the derivation of these. A little bit you're going to want to take this on faith, but if you don't want to, that's good. Take a look at a deeper probability book and you'll see where they come up with these derivations. And I'm going to first show you what these are in a little bit of a more physical kind of sense, as in not a symbol upon symbol upon symbol, although I'm sure when you first kind of look at this it looks that way. But I'm going to ultimately come back to you and connect what I'm doing here with what's in your Montgomery and Runger textbook. Right, so one of the things that we're going to need is the mean of the natural log of y. And remember, the expected value of a function is not the function evaluated at the mean, and that's the case here. There are two very simple direct results that we get for the mean of the natural log of y. One of them is that we can end up showing that the mean of the natural log of y is equal to the natural log of the median of y. Right? Not the natural log of the mean of y, but the median of y. It's also equal to the natural log of the mean of y minus 1/2 of the variance of the natural log of y. This is a mouthful to have to deal with here, and it's very subtle in its difference, and we'll do a numerical example here in a second that will illustrate how to work with these guys. The other one that we end up needing then is the variance of the natural log of y. Notice it shows up here just in trying to evaluate the mean of the natural log of y. And this one's a little bit simpler in its form. It's the natural log of 1 plus the COV of y, where I've used that simple delta for the COV. Right? In terms of what you have in your Montgomery and Runger textbook, the mean of the natural log of y is what they call theta, and the variance of the natural log of y is omega squared. And that's convenient for shorthand because you don't have all the subscripts running around, although it's not so convenient in terms of remembering what theta and omega squared actually represent. that theta is the mean of the natural log of y, and omega squared is the variance of the natural log of y. Now, in terms of the original variables, we can solve these and, in other words, manipulate these around a little bit, and we can solve for the mean of y, and that's going to be equal to e raised to the power of the mean of the natural log of y plus 1/2 of the variance of the natural log of y. In other words, you just solve this equation up here for natural log of the mean of y, and then you raise everything up to get rid of the natural logs, and that's how you get that one. The next one requires a little bit more manipulation to go through. The variance of y is equal to the mean of y squared times the quantity e raised to the variance of the natural log of y minus 1. Right, so you're only raising e to the variance of the natural log of y. You don't have the minus 1 is not up in the numerator of the exp. Right, so these are the equations that we're going to need to have accessible to us as we go about and get ready to do a numerical example.